4.1 continued, maximum and minimum values of a function. We have example 3. Find the critical values of h of x equals 1/2 sine of 2x. So I know how much you guys love trigonometry. We're going to get plenty of it in this example. So starting out with the basics here, to find the critical values of a function, all we need to do is take the derivative, set it equal to 0, and solve for x. Most of the time that's all we have to do, but we also do need to check where the derivative does not exist. So it doesn't come up a lot. Usually for you guys it's just going to be division by 0 is when you have to look out for that. So we'll start by taking the derivative. We have a constant multiple of 1/2, and then we have sine of 2x. We're going to use a chain rule. So we have cosine for the derivative of the outside, evaluated the inner function. Original one is 2x, and then we have to go ahead and multiply by the derivative of 2x, which is 2. So that simplifies to just cosine of 2x. And our next thing is we need to set, well, first of all, notice, I guess, that there's no x for which cosine of 2x equals dne, or where that function does not exist. Cosine of 2x is just a transformation of cosine, and it's just got a little bit shorter period. Other than that, it's not, it doesn't have any discontinuities or anything weird going on. So, next thing is let's set cosine of 2x, or the derivative, equal to 0, and see what we can get from that. So to do this exactly in radians, assuming that x is in radians, we've done this before, but we've never had a constant on the inside of the function here. So kind of different ways to do this, but the way I'm going to show you is, let's just say cosine of t is equal to 0 and figure out the solutions for that. And then we'll backtrack and say, well, actually t was equal to 2x. So we're just using kind of a dummy variable here to make it look a little bit more simpler in the beginning. Notice that in the original statement it says problem statement, it says find the critical values of the function, and it doesn't say on a particular interval, so we need to assume that we're going to do this for the domain of all real numbers. But let's just look at 0 to 2 pi initially for cosine of t is equal to 0. So I'm going to whip out my unit circle and think about, on 0 to 2 pi, where do I have cosine of t, or the x-coordinate, equal to 0. So that's going to happen at pi over 2, because at pi over 2 we have the coordinates of 0, 1, and cosine is the x-coordinate. So for t, pi over 2 is going to be one of the solutions. Now the other place where the x-coordinate is 0 is down here at 3 pi over 2. And so we have the coordinates of 0, negative 1 here. The x-coordinate is, again, the cosine. So on the period of 0 to 2 pi, we have solutions of pi over 2 and 3 pi over 2. So now let's go back and talk about t. So t is equal to 2x actually. So to relate for each of these back to x, just set up in a little equation is one way to do this, where, well, t is equal to pi over 2, which is 2x, so then the x here would have to be pi over 4. And then do this for the other solution we found in terms of t. divide both sides by 2, and we're going to get 3 pi over 4. So from trigonometry, you might remember that when we have a value on the inside times x, that changes the length of the period. And so the period here, it changes by a factor of 1/2 because it's a times 2 there. So whatever number is in front of x, you divide by the period of the normal base function of cosine is 2 pi, and divide that by that number. So the one down low is the 2 that's in front of the 2x here. So this is on a period now of 0 to pi. For x equals pi over 4 and 3 pi over 4. So that's important because now when we generalize our solution, we've found everything for one period of cosine of 2x, and then we need to generalize. So pi over 4 plus, instead of 2 pi k, is going to be pi k, because this is the period that goes here, times k. And then our other one is going to be 3 pi over 4 plus pi k, where k is an integer. Now this would be full credit, but I'm just going to show you how to make this even more simplified in this case. So if we notice here, let me kind of show you where this is at on the unit circle. It's one way to handle it. That pi over 4, this is the world's worst unit circle. I will start over here. So pi over 4, that's one of our solutions, and again our period is 0 to pi, and the other solution from 0 to pi was 3 pi over 4, which is over here. And so notice that if we count by pi's over 4, we get pi over 4, and then we have 2 pi over 4, which is pi over 2. Add another pi over 4, you get to 3 pi over 4, add another pi, you get to 4 pi over 4, which is pi. I don't know what just came out there. 4 pi over 4, which is pi. So actually we can reduce this a little bit more even if we're crafty, and again this is for style points, which don't count for anything. If we notice that I'm going by a quarter here, and then I'm moving to the next solution, well, okay, I'm jumping here. So what would the other solutions be? Or let's work out maybe k equals 0, k equals 1, etc. So if k were equal to 0, the solutions we would have here is pi over 4 in this first one, and then we'd have 3 pi over 4. For k equals 1, we would have 4 pi, we're just getting pi over 4 plus pi. So let's simplify that. It would be pi over 4 plus 4 pi over 4, which is 5 pi over 4. And so let's put where that would get us right here. And then for this other solution, if we had 3 pi over 4 plus pi for k equals 1, that would be 3 pi over 4 plus 4 pi over 4, which is 7 pi over 4. And that is over here. Okay, so this is just writing down more of the solutions to see if you can generalize and compact this down to a solution that's together. So notice these are the solutions and they're equally spaced, so that means we can reduce it just to one answer. That's what I was trying to get to here. So if we take, these are the solutions, I have other things labeled here. The with the points. So they're all a distance of pi over 2 from each other. So we can put this together, reduce to x is equal to pi over 4, and then instead of plus pi k, you can do pi over 2k, because all these solutions are a distance of pi over 2 apart, and then we'd cycle through. So you could verify by letting k equal 0, 1, 2, etc. to see that, hey, you get all those. So this is, again, more simplified, but a little beyond my expectations, but good to see. So anyway, back up here would be a good enough answer. That was actually the answer. Trigonometry for this one was kind of involved, but good practice. So let's move on to another example. This is example 4. Find the absolute extrema of g of x is equal to the third root of x squared times the quantity 2 minus x on interval -1 to 2. So to find the absolute extrema, the first step was to find the critical values. So that's where we're going to take the derivative, set equals 0, solve for x, and then we also need to look out for where the derivative does not exist and solve for x when that occurs. So let's start with our derivative. So here, notice that before I launch into the derivative, maybe I want to simplify. There's actually some problems where maybe it helps to just do the product rule directly, but for this one, I'm just going to go ahead and simplify first. I just mentioned that because I'm trying to illustrate the fact that, or not illustrate, but tell you that sometimes it actually pays to leave it in that form. So I'm just distributing the x to the 2/3. New power here, x to the 2/3 times x to the 1, add 2/3 plus 1, and we're going to get 5/3. And so now that derivative is easier to take. Do it. So I have 2, constant multiple rule, times the derivative of x to the 2/3, so bring down the 2/3. X to the new power is -1/3, minus power rule for this one as well, 5/3 x to the 2/3. Okay. Alright, so we're going to set this equal to 0 and try to solve for our x. But I try to highlight the fact that we should be looking for where the derivative does not exist first, just to either dismiss it or handle it right away, because it's easy to forget to look for it at the end. And so just looking at this, notice that whenever you have negative exponents, you're automatically going to have a place where the derivative doesn't exist. Why am I canceling those out? That's not good. I'm trying to do two things at once. So here we have a negative exponent, which can be written differently, where we have the x in the denominator, and then you can see why we would have division by 0 or a place where this derivative does not exist. So just to highlight that, I'll write it as 1 over x to the 1/3. And now note that when x equals 0, we get this term does not exist because of division by 0. So for a critical value, we already have something on our list. We have x equals 0 from that. So now let's address when g prime is equal to 0, because we might get some critical values out of that. So 4/3 times x to the negative 1/3 minus 5/3, oops, x to the 2/3. You might try a couple different things here on how to solve this. Because we have two terms with x that have fractional powers, this is a little tricky. So kind of the best way I can explain this is to do the following. This will work every time. When you have fractional powers, with at least one being negative, so notice we have two fractional powers in this. I'm identifying the one that's negative. Turns out a good thing to do is to factor out the negative power from both terms. And then while you're at it, take out any fractional constants. I'll just put in fractions. Now, what does that mean for this problem? This means that x to the negative 1/3, we're looking at the negative 1/3 power, and it's easy to know how to factor out this power from both terms. We're going to just leave a 4/3 in there. But what about the x to the 2/3? So in other words, x to the 2/3 is equal to x to what power times x to the negative 1/3. So that question mark is the correct power that when we put these together we get 2/3. So notice that the operation here would be addition with our exponent rules. So we could just solve this handy dandy little equation, add 1/3 to both sides, and notice that the question mark is 1. Or that power would have to be x to the 1. We can just verify that by adding those, and yeah, you get 2/3. So however you want to figure it out. But now I'm going to go back to the problem. I have x to the negative 1/3, which I'm going to take out, because I didn't really need those parentheses. Minus 5/3. And then I'm going to write this, instead of x to the 2/3, as x to the negative 1/3 times x to prepare it. Like I also said, take out any fractions overall. And so notice 1/3 is a common factor. Take it out, and I have 4 minus 5x. Oh, whoops, except I need to actually take out the x to the negative 1/3 instead of pretending I did. So 1/3 x to the negative 1/3, sorry about that, and then we're left with a 4 for the first time, minus 5x. Now this is where the magic happens. As a fraction we have 4 minus 5x, and then it's over 3x to 1/3. So on the bottom is where we have division by 0, and we already determined that x equals 0 is a critical value. But we can see it again here. I'm ignoring the fact that I already set the left-hand side equal to 0. So just note that the division by 0 was accounted for above. We got the x equals 0, it's a critical value. Now the part we care about here is the fact that what contributes to g prime being 0 is the top. The top can be 0, and that would mean we have 0 divided by some value, and that's 0. So 4 minus 5x is what we need to solve, and we get x is equal to 5/4 from that. So that is our, just kidding, not 5/4. Maybe I should just do the math instead of trying to be fancy and do it in my head. Sorry about that. 5x equals 4, so x equals 4/5. Good. So this is another critical value. So overall, our critical values are x equals 0 and x equals 4/5. So, it seems like we should be done, but we've only just begun this problem. We were doing that to try to get at the absolute extrema of that function on -1 to 2. So, next thing. When we find absolute extrema on a continuous function, for a continuous function on a closed interval, we can use the extreme value theorem, which says other candidates for the extreme values, or maximum, absolute maximum, minimum, are also the endpoints. So those were -1 and 2. And notice that these values, the critical values, are on the domain, and so we include them. If they were outside the domain, or outside of -1 to 2, then we would just throw them out because we're not looking there. So I'm going to organize a little bit of a table here. Left to right, -1, then I had a critical value 0, and then the next value was 4/5 from left to right, and then finally 2. Again, because I'm just finding the absolute extrema and not the relative mins and max, then I can just do something here where I am checking to see what's the highest y and the lowest y. I'm guaranteed to have extreme value, and we have the candidates for it. So the answer will become apparent from this. Again, we're using the extreme value theorem. Here's kind of our legit thing we're doing. Notice this is not f prime, this is the original function, which was a long time ago. I'm going to write it out. So using our function, which I renamed f because I'm on autopilot, so g was 2 x to the 2/3 minus x to the 5/3 in one form. So if you plug in -1 into that, you get 3. If you plug 0 in, you get 0. For 4/5, you get about 1.03. So approximate answers are okay here because we need to compare them and see where they are relative to other values. And then we have x equals 0. So for the absolute minimum, we have a tie in this case because these are the two lowest y's. So absolute min at, and you have the coordinates from this too, which is nice, so 0, 0, and 2, 0. The highest value is the absolute max. And we only have one of those. There's no other y coordinate of 3, so we don't have a tie. So absolute min at -1, 3. And I think that's all we had to do. I'm just going to show you the graph quickly. We're not to the graphing yet, but we're going to get there really soon in the next section. And I also want to show you why, for the first time, the derivative does not exist, why that should be considered as a critical value, meaning why is it a candidate for an absolute max or min or relative max or min. So this graph is really funky. We don't have, again, enough information to draw this graph with the correct curvature and stuff, but this is what this thing looks like. And highlighting a few points here. This is -1 to 2, which obviously this is way out of scale. So bear with me on that. But this is what's going on here. And so the place at which we had division by 0 was this really abrupt change in the graph, which can happen when you have fractional powers. So this is not a polynomial function here, because we had those fractional powers, which means we got some root action in the original function. And so you can have some kind of crazy stuff going on here with regard, and this is like a cusp. Here's what this is. So this was our absolute max, and we had a tie for our absolute min. So that's just showing you, hey, when you have the derivative dne, it turns out you can have a relative max or min there. So that's a place we have to check, and this is what happened in this graph. That's it.